Hello everyone, and welcome back to another cartography lecture video. And in this lecture video I want to pick up where we left off, talking about projections, and take what we talked about last time, which was this idyllic case of latitude and longitude, and add some wrinkles to it that really have a pretty major impact on the accuracy of measurements of location on the Earth, and have a big role when we talk about projections. And so to sort of recap, in the previous video, we talked about this idea of latitude and longitude, and we described how they were simply angular measurements relative to a coordinate system that was set up using the equator and the prime meridian. And that you could measure east and west of the prime meridian with longitude, and you could measure the angle north and south of the equator with latitude. Now, the big issue that we run into here is this assumption that I made in the beginning of the video where I said that we were dealing with a perfect sphere. If you spent any time with a globe, you might have felt, especially if it's one of those ones that has the topographic relief added, right, you might have felt those little bumps and valleys that were caused by interactions with tectonic plates, and even more importantly than that, the fact that the Earth's crust is not uniform in its consistency and composition. Right? It might not come as a surprise to learn that the Earth is not a perfect sphere. Right? The Earth is not a perfect sphere. And it's not a perfect sphere in two key ways. The first is that the Earth is lumpy. Now, when I say lumpy, you might be thinking about the mountain ranges and the ocean trenches. So of course you're like, oh yeah, the Earth is clearly not a smooth surface. But it goes far beyond that. The composition of the Earth's crust is different both in terms of ocean crust versus land crust, continental crust, but also even within that, there are differing compositions. And those differing compositions mean that they're affected by gravity in different ways. So the Earth is lumpy. So instead of looking like this, right, now again, this is going to be exaggerated, right? It looks more like something like what you might see in a game of asteroids. And so you can imagine that this right here would make wildly different measurements of latitude and longitude depending on which part of the lump you're measuring from. Now, thankfully, we have had a lot of time to study the lumpiness of the Earth, and we're able to create mathematical models of this lumpy Earth that are called geoids. Right, a geoid is a mathematical representation of the Earth lumpiness. Now, you'll oftentimes hear a geoid in the context of if the sea were to be able to flow freely over the continents. The technical definition of a geoid isn't super important for this context. It's just important to know that our perfect idyllic spherical Earth doesn't work. And one of the main reasons is because the Earth is lumpy. The second key deviation from this idea of a perfect sphere is not only is it lumpy, and again, this is an exaggeration of the lumpiness, but it's also squished at the poles. Right? It's squashed at the poles. So to put that another way, the Earth is wider at the equator than it is going through the poles. Or to put that yet another way, right, the diameter of the equator is greater than the diameter of the prime meridian. Okay? So to sort of state that in picture form, right, again, our assumption here was that the Earth is this nice, perfect sphere here. When in reality, again, I'm exaggerating this slightly, the Earth is more like this. Right? And so if you spent any time in geometry or algebra 2, you hopefully might recognize that when you take a circle and you squish it, you end up with what's called an ellipse. Right? An ellipse is what happens when you squish a circle. So the Earth is actually, if you were to cut it cross-sectionally, is actually an ellipse. And when you take an ellipse and you sort of put that concept into 3 dimensions, you get what's called an ellipsoid. And an ellipsoid is actually another mathematical representation. But this is a mathematical representation of the squashedness. Right, squashedness, technical term, of the squashedness of the Earth. Now, the nice thing about an ellipsoid, compared to a geoid, is that an ellipsoid is something we can actually use to calculate our latitude and longitude. Right? An ellipsoid is a fairly, relatively speaking, simple mathematical framework for understanding the Earth. And so if we assume here that the lumpiness can't be accounted for easily, with the ellipsoid we can actually start to use this ellipsoid as a model framework for our latitude and longitude. Okay? So what we're going to be doing in cartography is we're going to be seeing coordinate systems that are going to have ellipsoids, or ArcGIS Pro for some reason likes to call them spheroids, probably because they're fairly close to a sphere. Again, this was highly exaggerated. But again, right, we can do all kinds of mathematical representations of an ellipsoid. So, geoid, lumpy, ellipsoid deals with the fact that the Earth is squashed, and we can use this ellipsoid as a framework for doing our latitude and longitude calculations. Now, what I want to do here is I want to introduce a third concept. So these two have to do with the Earth not being a perfect sphere. I want to introduce another concept called a datum. And so you can imagine, as with many things dealing with math, right, we have parameters to these mathematical representations. And so ellipsoids, just like any other representation, we can tweak the parameters. And so you can imagine if we have a geoid, which I will draw here in blue, right, again, I'm exaggerating slightly here, right, if this is our geoid, right, if we were to draw an ellipsoid, or create an ellipsoid, right, you can imagine we can create all different kinds of ellipsoids. Right, we could create one that looks like this, right, we could create one that looks like this, by changing the parameters that go into the definition of this ellipsoid, right, we can tweak the shape of the ellipsoid. And what I want you to pay attention to here is the fact that each of these different ellipsoids interact with this geoid in different ways. And hopefully this will be intuitive to you, but you can imagine that the closer the geoid is to the ellipsoid, right? So for example, in this point right here, where the geoid and the ellipsoid match, right, this is going to be where we have the most accurate possible representation of the geoid, which again is a mathematical representation of the lumpiness, by this cleaner model that we call the ellipsoid. So this is going to be our best possible accuracy for latitude and longitude. And so you can imagine that by tweaking these different parameters of the ellipsoid, we can create different ellipsoids that are going to match the geoid differently. And so what I'm trying to get at here is that different regions, say North America, Europe, Asia, right, they might use different ellipsoids to define their projections, because different ellipsoids are going to interact with the geoid differently. So you end up with things like the North American datum, NAD, right? We have 83 for 1983, and we have one from 1927. So you'll see NAD 83 and NAD 27 come up a lot when you're dealing with data from North America. You'll also see WGS 84 come up a lot. WGS 84 is actually the one that most GPS units default to when we're dealing with collecting data, raw data from GPS units, right? And what these are just saying is that they've picked a geoid that is optimized, in this case for North America, and in this case WGS, the World Geodetic Survey, is optimized, or should I say a compromise, so that you get the least amount of distortion for the entire world. Right? And so this combination of where the ellipsoid matches the geoid, right, this is what's called a reference point. Right, where the geoid touches the ellipsoid, right, that's a reference point. And the reference point is going to be different for each datum. And every other location, let me make this clear here, every other location is based on this reference point. And this reference point is going to be different for each datum that we have. Okay? Let me repeat that one more time. The datum is the relationship between the geoid and the ellipsoid tied through the reference point, which is where the geoid and the ellipsoid interact. And each datum is going to have a different reference point, and it's going to be optimized for different parts of the globe. Okay? Now the nice thing for cartographers is that we largely don't have to deal with too much of the datum aspect of it. We just have to make sure that all of our data is in the same datum before we work with it. Okay, so hopefully this made sense. This idea that we have a lumpy geoid, a smooth ellipsoid, we can tweak the parameters of the ellipsoid to match the geoid in certain places on the Earth, and where they interact gives us a reference point. That whole interaction is called a datum, and we have different datums for different places on the Earth. So hopefully that all made sense, and as always, if you have any questions, please reach out. Thank you.